just like all of the functions that pass through the same point that have derivatives in the same?
Yeah.
Okay.
But it's not just pointwise addition of functions. It's basically, the basic idea here is we're adding the vectors that the curves represent. But actually putting pen to paper to make that explicit is not entirely easy. Unless you think of a more clever notation than I have today, which is entirely possible. Maybe it's in John Lee's book.
That last thing that you wrote makes more sense to me, the green.
Yeah, so that, basically, I'm proposing that like there's a correspondence. Gamma corresponds to a line in the down here whose direction is given by the velocity of gamma up there. But this is all done with respect to one choice of coordinates, right? So I think if I thought about it more, maybe I should show that. Well, anyway, let me not think more about this. Enough about this. Listen, the long story short of it is we are going to use the equivalence class of curves viewpoint for tangent vectors when it suits us. A primary example for you would be proving the chain rule for problem 17, because it becomes 3 lines if you use this formalism. You just need to use this. Because when you have f composed with g, df composed with g, I'll get you started on it. Like d of f composed with g, if g, these are 2 smooth maps, right? If you let that act on gamma prime of t naught, that is then equal to what? F composed with g composed with gamma prime of t naught. And if you just sort out what that means and apply this proposition again, you should be able to like derive the chain rule without a lot of fanfare.
So if your domain is Rn,
Mm-hmm.
and you're trying to add your like equivalence classes of the derivatives,
Yeah.
In order to get the whole space, how many do you need to add? Is it 2 that aren't parallel?
Ooh, how many equivalence classes of how many distinct equivalence classes of curves at a point do I need to get the whole space?
Yeah.
N.
N?
If it's an n-dimensional manifold.
Okay.
Right. Yeah. But I mean, do you agree with me? Like, this is by far the most challenging problem of vector addition I can think of. It's quite horrible. The closest thing to it is like, if you think about Rn, a linear manifold to Rn is something like this, right? So there's like a base point P, and you can think about like the vectors attached to P, like that. We actually kind of already talked about this at the start of everything, right? The vectors attached to P, how do you add them? You just add the vector parts. Like every vector is P comma V or P comma W, so to add those, you just V plus W, the P stays fixed. And this is somewhat akin to that problem, but it's just a little bit more soupy because of the formalism. All right, so the only thing that remains in chapter 3 for us to talk about is the tangent bundle. So just to give you, a very quick rundown of what that is, the tangent bundle is a new manifold where what we do is we take all of the tangent spaces to the manifold and just think of them all together at once. In quote of something called, it's called the disjoint union. So we take the disjoint union of all the tangent spaces, and this is called TM. So like, there's really not much to say about the tangent bundle for you guys at the moment, but it's just TM, and this is the notation for disjoint union, P and M, TPM. So what that means is that like a typical point in the tangent bundle is something like P comma V. Have you guys ever seen disjoint union before?
No.
Do you have any idea what it means? So, for example, the disjoint union of R with R is not equal to R.
What is it equal
Well, it's a good question. I think essentially,
to? Is it like anything?
I think you could think of it as, I think you could think of it as the Cartesian product.
Why wouldn't you write Cartesian product?
Because you'd like to think of it as the disjoint union.
Is it like R minus a point?
Because it's not the Cartesian product. So this is, all right, fine. Let me try to formally define disjoint union, start our next class. All right, this, because I think you're justified in your, what is that? That's fine. Start first order of business next class, define disjoint union carefully. I may regret that. Now, once you understand what that is, which in a nutshell is really just thinking of taking all of these together as a space, but at the same time not identifying them. In other words, like the tangent space at P1 and the tangent space at P2, we're not like putting them together as one space. In the same way I write different RNs for my different coordinate charts, like separate them, that's kind of the same idea. I could always just make all the coordinate charts go to the same RN, couldn't I? You know, pictorially. That's the tangent bundle. That's the tangent bundle. And then the question is like, what's the coordinate chart on the tangent bundle? So phi usually, I think uses phi tilde of PV. Supposing that, you know, U phi is an element of the atlas for the smooth manifold, you know, with or without boundary. Phi tilde of PV, how do you define the, he calls this the natural coordinate chart. The natural coordinate chart. You could also, in my class, when I took manifold theory, we called it the adapted coordinate chart. Because it's a coordinate chart on the tangent bundle, which is adapted from the manifold. And the adapted coordinate chart is very dumb. All you do is you take phi of P, and then V1, V2, Vn, right? Or in my notation, this looks like, I like my notation better, x of P, and V of x1, V of x2, V of xn, where of course I'm using the notation that phi is equal to, you know, the x coordinate, phi is equal to the x coordinate chart. So this right here is in Rn, right? This altogether is also in Rn. So what are we looking at? We're looking at our n plus n, 2n. So the tangent bundle to a manifold is a twice the dimension of the manifold on its own right. And John Lee carefully explains why it has all the necessary topological property. It's Hausdorff. It's, you know, these give you local homeomorphisms to R2n. All right. And then if you were to take if you had, you know, two different adapted charts, two natural charts, which were both defined at P, the rule for changing coordinates from one to the other would be given by a transition function for this and the change of variables rule for the components of a vector for that, which is why I wanted to talk about this today, because we derived it today. But the change of coordinates formula for a vector was just, what is it? It's just partial x bar I, partial xi summed across the components of the other vector, right? But the thing is, the partial derivatives of the one coordinate chart with respect to the other themselves are smooth functions by assumption of the structure of the manifold. So like it's obvious then that the transition functions for the adapted coordinate charts are themselves smooth. Lo and behold, the tangent bundle is a 2n dimensional manifold that you can construct from any manifold. It becomes very interesting as we go on to study the tangent bundle. The question is, if the tangent bundle is actually equal to the Cartesian product of the manifold in Rn, then the tangent bundle is said to be trivial. So if you had one coordinate chart which covered the whole manifold, like if you had a global coordinate chart for your manifold, it turns out that that means that the tangent bundle is it's diffeomorphic to the Cartesian product of M and Rn. And that is equivalent to the existence of a non-zero vector field on your whole manifold. So existence of non-trivial vector fields over the whole manifold is an interesting topic in and of its own. So we'll be talking more about these. I just wanted to throw out, just to get us started, like that's what the tangent bundle is. There's really not much more than that about the tangent bundle in chapter 3. So we're nearly on pace for what my course planner said. So I'm not going to abandon the plan just yet, but I'm always sympathetic when you guys need a couple of extra days, but don't take a couple of extra weeks because then that won't work in the end. But anyway, and I would say I will try to end class on time, but it's just not true. Sorry, Ernesto, but you could have watched this on double speed. So, oh my, ooh, ouch.